2022 projectile motion. A steel ball was held 40 centimeters above the table. The ball is released and the time for it to fall to the table is measured. Calculate the time it takes for the ball to fall to the table. All right, first things first, let's figure out what we have here. So we've got our little table of our horizontal values and our vertical values. We keep them separate, okay? And so right now, let's deal with the vertical height. The vertical height that we've been given is 40 centimeters. We need to convert it to meters, and so that's going to be 0.4. So we know the distance, the vertical distance, is 0.4 meters. We want to figure out time. The initial velocity is going to be 0 because at the top over here, there is no motion. It's at a standstill, so the initial velocity up top is 0. Final velocity, we don't know if we'll actually need it, but we know acceleration is 9.8 meters per second. I want you to take some time, have a look at your resource sheet, pick out the equation which includes these values over here. I'm assuming you've gone ahead and done that. The values that I'll be using, the equation that I'll be using is D equals VIT plus half AT squared. Before we go ahead, we need to define our positive and negative vector values. So let's have a look at this diagram as a reference. I want you to remember that our velocity, whatever direction it's going in, whether it's up or down, I suggest that you always define it as a positive value. So the velocity is going to be a positive value. Then we look at gravity. Is it opposing or not opposing the direction of our velocity vector? Well, gravity always acts down, always. Is it opposing the direction of our initial velocity? No, it's going in the same direction. So it's also going to be positive, okay? So if we look at our equation, nothing's going to be opposing, okay? So all the values in our equation are positive. VI is positive, acceleration is also positive. Easy peasy. Then we can simply substitute everything that we have in. So the distance is 0.4. VI, our initial velocity, is 0 times t plus half a 9.8 times t squared. All right, next step is to simplify whatever we can. We know that 0 times t is just going to be 0. Half times 9.8 is going to be 4.9. And so we can go ahead and rewrite this equation to make it less clunky. So we've got 0. We're not going to write that in. Plus half times 9.8, which is 4.9 times t squared. Nice. So what we can do now is we need to get rid of the 4.9 so we can get t all isolated. All right, the time all isolated. To get rid of 4.9, we have to divide it by itself and then do the same on the other side. Then what we're left with is t squared equals 0.4 divided by 4.9, and that equals 0.082. But we don't want the time squared, we want just time on its own. So to get rid of this square, what we do is we square root this whole thing on both sides. So we'll be left with t equals the square root of 0.082 in your calculator, you should get 0.286 seconds. Don't forget units, okay? So, this answers part A, okay? The time taken is going to be 0.286 seconds. All right, so next question, moving on. The experiment was repeated with another ball of the same size, but half the mass. Ignoring any effects of air resistance, use physics principles to explain how the time for the second ball to fall compares to the time of the first ball to fall. Okay, so let me try explain. We're ignoring air resistance, okay? And so I want you to think back to the start of the year when I showed you that classic video of the bowling ball and the feather. So they put 2 and 2 side by side and then dropped these things. With air resistance, the bowling ball would have reached the ground faster because it has a heavier mass. However, when they've removed all the air so that there was no air resistance, both the bowling ball and the feather fell to the ground at the exact same rate. This is because gravity has the same effect on both objects. Considering this context over here, we've got 2 balls. One of them is half the mass. Since there's no air resistance, both balls would actually fall to the ground at the exact same rate. Okay, the time taken for both, even though they have a different mass, both will fall at the same rate. So this is something that you can write. And there we have it. Okay, so that's part B answered. Let's have a look at the next question. Okay, the steel ball is now rolled along the table and off the edge as shown. The height of the table is 70 centimeters and the ball hits the ground 1.8 meters past the edge of the table. A. Calculate the ball's final vertical velocity. What assumption have you made? Okay, so let's start off by figuring out all the things that we have again. This is the way to tackle these types of questions. Always figure out what you have and what you don't have. Since we're wanting to find the vertical velocity, we're dealing with the vertical component of our table. Okay, so we're dealing with this right over here. So we want to figure out, the question wants us to figure out VF. What else do we have? Well, we have the vertical distance that this ball is going to have to fall, and that's 70 centimeters, aka 0.7 meters. Okay, convert centimeters to meters. Acceleration is 9.8 meters per second. What else do we have? What's our VI? We assume that the initial velocity at the top of the table is going to be 0, okay? And what else? Pretty sure that's all we actually need. We don't know the time, maybe we won't need it. So based on these values here, what is the most appropriate kinematics equation to use? Give you a chance to see what you use. So I reckon it would be safe to use this kinematics equation right over here. VF squared equals VI squared plus 2AD. And so now what we have to do is define what our positive and negative values are. So if we look at the diagram, we see that the velocity will be going down and so will gravity. So both values will be positive. So nothing really needs to change here. We're all good to go. We can substitute everything that we have. So Vf squared. What's our final velocity? This is what we're trying to find, so we don't substitute anything into that. Initial velocity is 0 plus 2 times 9.8 times the distance of 0.7. Okay, let's simplify this thing. So Vf squared, 0 squared is nothing, so we don't have to include this in the equation, plus 2 times 9.8, okay, times 0.7. All of that times together, okay, if we simplify this part over here, we get 13.72. So that is the final velocity squared, but we don't want the squared answer, we want the unsquared answer. So to unsquare, I'm going to take the square root of both sides. So we're left with Vf equals 3.70 meters per second. Okay, so that is the final vertical velocity of this ball. This is the final vertical velocity of this ball. So the next thing that we have to figure out is, what is the assumption that you have made? Well, you should write down or understand that there are no external forces acting, okay? So there is no air resistance, and the acceleration of this ball is purely because of gravity, nothing else. So feel free to write down what I've just said. Moving on to D. Okay, calculate the size and direction of velocity of the ball just before it hits the ground. You should start by showing the horizontal velocity of the ball is 4.8 meters per second. So I just want to put this into a diagram. Okay, so what we have here is we've got the ball up top, okay? And it's got this resultant velocity in this direction, okay? So this is V resultant. Another thing that we have, okay, is our vertical velocity, V vert. And we've just figured that out to be 3.7, I'm going to put the unrounded answer, meters per second, okay? So that's the vertical velocity that we've just figured out. We want to start off, the question has told us we need to start off by figuring out the horizontal velocity, okay? And then we can figure out the final velocity just before the ball hits the ground, right over here, okay? This is what we want to find out. But we first need to start here. So what are we going to do? What are we going to do? Well, remember, in our table, when we're dealing with the horizontal, the equation that is only applicable in this section is V equals d over t. This is the equation for constant velocity, and we know that the horizontal component is always going to be constant. So, to figure out V horizontal, we need distance and we need the time, okay? So we know the distance. Let's have a look at the question. The distance is 1.8 meters, okay? We know in this equation, distance is 1.8, okay? That's how far the ball hits or lands from the table. That's how far the ball lands from the table, okay? All we need is time, and then we can figure out this horizontal velocity. All right, so let's go do that. How do we figure out time? I want you to remember that time is the linking factor between our vertical and horizontal, okay? The time taken for something to fall vertically down is the same time taken for it to go horizontally across, okay? And I proved that to you in class with that video that I showed you earlier. Okay, so how do we do this? What do we have to do? Well, I already know VF vertically, okay? VF is 3.7. I know, what else do I know? Initial velocity was 0, okay? I know the acceleration is 9.8, and time is what I'm trying to figure out. So, the time taken is what we're trying to figure out, and so the kinematics equation that I'm going to use that involves all of these things is going to be VF equals VI plus AT. Then I can rearrange to find time. So VF is 3.7, VI downwards, okay, is 0, and we know the acceleration is going to be positive because it's also acting in the same direction, plus 9.8 times t. Simplifying that, 3.7 equals 9.8 times t. Divide both sides by 9.8 to get t by itself. And the answer for time taken for it to fall vertically downwards is 0.3776 seconds. So I know now that this time value, okay, can be used not only for my vertical, but I can use this for my horizontal. And so finally, I can add that to my equation. So V horizontal equals 1.8 meters divided by 0.3776. And I know that my horizontal velocity is going to be 4.77 meters per second. Okay, so my horizontal velocity, okay, is going to be, let me write it in here, V horizontal equals 4.77 meters per second. Okay, let me highlight that. So we've done that part of the question, we've worked out the horizontal. What we want to find out now, let's have a look. It's asking us, we need to calculate the size and direction of the velocity of the ball just before it hits the ground. So the final velocity over here. And it's not the final vertical velocity this time, it's the resultant, okay? It's the final resultant velocity. So how the heck do we do that? Well, as you can see, this is a bit of a triangle. Got a squared plus b squared equals c squared. So I'm going to make this right over here I don't want to use that, a squared. This right over here is my b squared, and this value that I figure out here will be my c squared. Okay, so let's go ahead and do that. A squared is going to be 3.77 squared plus b squared, which is 4.77 squared equals c squared. Okay, so plussing these values in my calculator, I am going to get 36.44 equals c squared, but I don't want c squared, I just want c, so I'm going to take the square root of both sides, and what I'll have here is c equals 6.1 meters per second. Okay, so 6.1 meters per second. That's my value here. Okay, so now what I can do is, read the next part of the question. So I've calculated the size. So on its downwards journey, we've just calculated that the final velocity just before the ball hits the ground is 6.1. Now what I need to do is I need to show the direction of the velocity. And the way we're going to do that is by working out this angle here. This will tell me the angle that the ball is going down at. So how do I do that? Well, now what I can do is a little bit of trig. So how do I figure out the angle? What I'm going to do is I'll label my triangle. So this right here is going to be my opposite. This right over here is going to be my adjacent, okay? And this right over here is my hypotenuse. So I'm going to use the values that I've already been given or calculated prior, okay? So 3.77 and 4.77. And so O and A are the things that we're concerned with. So if we're using O and A, the trig function that we'll be using is tan theta, okay? AKA toa, from soccer toa. Okay, so let's go ahead, use the equation, tan theta equals O over A, substitute what we have in, we've got tan theta, that's what we're trying to figure out, the angle to show the direction, equals opposite, which is 4.77 over 3.77, and we need to rearrange this thing to find this theta angle. So what we have to do is we have to take the inverse tan, okay? So theta equals tan inverse 4.77 over 3.77, and we will figure out by plugging that into the calculator that the angle that this ball is going down at is 52.4 degrees. Do not forget the little symbol of degrees. Okay, so we know that the size of velocity just before the ball hits the ground is going to be 6.1 meters per second, and then the direction is going to be going down at 52.4 degrees. Boom! Well done for making it this far. Hope it all made sense. If you have any questions, email me.